Hello everyone, my name is Brad Erickson. I'm the director of the Mayo AI Lab, and I'm going to do a quick introduction to the issues of probability, calibration, and certainty as it applies to AI models. For those of you who have developed deep learning models, you know that at the very end we typically have this fully connected layer and use a softmax function to produce what are called probabilities at the output. In the AI world, that ultimately means then that the sum of these so-called probabilities add up to 1, and that sounds really very nice. The problem is that those probabilities actually should not be thought of as probabilities, but really more as ranks or scores, because the inference data, the examples there, do not reflect the same distribution, and therefore the probabilities are very different. That's going to be the focus of this talk. So let's go into that a little bit more. So can you make that output number be a probability? And if the data matches the training data distribution, then yes, and that would be known as calibration. So let's talk a little more about calibration. A model is considered calibrated when the probability estimates of the model reflect the true distribution of the outcomes. So for those of you who are familiar with MedNIST, where we have digits, this is a simple example where we use a classifier trained for MedNIST, and we have the numeral 1 here, and we're going to rotate it through 180 degrees. And you can see that as you rotate it, the output of the model is changing from being highly certain that it is the numeral 1 to then it thinking that it's the numeral 2, and then pretty sure that it's the numeral 5, and then back to being the numeral 1 again. And of course, you know that this is the same digit, and so the model is obviously giving you wrong values, even though that is what the model is trained to do. And so what we need to do is to introduce an element of uncertainty and say, for these angles of rotation here where the 1 is turned on its side, we really have a low confidence of whether it's a 1 or a 2 or a 5. And instead now we have a much higher value for uncertainty. And that really reflects the real life that we deal with in radiology. Now, we also have to think about what the probabilities are. The output probabilities can only reflect the probabilities of the classes that the system was trained on. And so if there's some disease or class that was not in the training set, well, there's simply no way that that could ever have the correct probability. So for instance, if you have a classifier trained to differentiate dogs and cats and then provide a picture with both, you're going to get garbage out of that prediction. And that raises the issue of out of distribution. So data used for training a machine learning algorithm or model has a certain distribution. We know that a certain amount of data will be in a certain part of the range. Now, what happens though when you have a single example that's very different? Well, that would be called out of distribution. That's, for instance, if you train a classifier for traditional bacterial pneumonia versus normal, and now you have COVID examples coming in, that's going to look very different, and you can't rely on those predictions. But another problem is that if you do have a whole new disease like COVID coming in, or a different imaging device, you're going to have a shift in that whole domain. And that's also a problem for your classifier that was trained on the previous distribution. So this is the problem of having out of distribution data. Closely related to that then is uncertainty quantification. So when an ML model makes some sort of prediction, it outputs the score for the classes that we were trained on. Now, if the model is calibrated, as we said, the score is then the probability for each of the classes that it was trained on. So that reflects the training distribution. But those predictions may have high or low uncertainty, and that's going to be independent of the probability. And this really reflects the inference time confidence. And so evaluation of a model's performance really needs to include both the model's predictions, the calibration, as well as the uncertainty for a specific inference example. So the things I want you to remember are that the predicted probabilities of deep learning classifiers should not be confused with their level of certainty. Training of DL models should include components to improve the model's calibration, And really, the uncertainty of DL models should be more frequently evaluated and reported in the literature and also in clinical use. Thank you, and I hope that you found this useful.